this is just going to be quite a short talk. It's quite a short project. This was. It's a sub-project that was done last year sometime for CPDN. This was done in conjunction with Suzuki and Saw Robotics. I think two other projects also worked with Suzuki. So you can see me, hear me, and you can see the presentation. Is that correct?
Yeah.
Great. Okay. So this is the outline of the talk. I'll just briefly introduce climateprediction.net, the outline of the work project, and the requirements we needed for the application itself, and the steps to support it, and then the results of this project, sub-project. So climateprediction.net has been running for a number of years now. It's a BOINC project. We use very large numbers of ensembles of climate simulations to produce to do climate simulations, ensemble climate simulations. So it's been using BOINC for a number of years now. So CPDN, so I'll use the acronym CPDN for short, instead of climateprediction.net. So in this project, the whole idea of the project was to explore the idea of running these climate simulations on the CAN bus, the central CPU unit within cars. And so the idea was that that these simulations would be downloaded when the cars are idle or they're being charged. So maybe would be computed overnight, not whilst the car is driving. These CPU units are across many manufacturers, are increasing power with time. So presents quite an opportunity for compute. So the whole idea of it, this is the flow diagram, just of the process that the car would, the BOINC client running on the car would download the simulation and the work, do the work, and then send the results back to the main servers. These are the Oxford-based servers. So now, for that we needed, we have a number of applications, a number of models, climate models we run in climateprediction.net. And we needed, so this model needs, there's a number of requirements for the model for this project. So these are listed here, what requirements were for, primarily things like the minimal dependencies, reasonable data volumes, it's scientifically useful, produce scientifically useful results, and scalable and short execution times. So for all of these, the sub-project OpenIFS at home, it fits ideally for this. The OpenIFS at home is a sub-project that's been running for a number of years now, a few years now within CPDN. It uses the OpenIFS model, which OpenIFS code, which has been produced by the European Centre for Medium Range Weather Forecast, which itself is derived from IFS, which is a numerical weather forecast model, which has been specifically produced for. So this has been specifically produced for universities and research institutes. The use of one of the key things of this is got a large user community of atmospheric scientists. And so that was the key plan around OpenIFS at home. So the idea that OpenIFS at home runs primarily at the moment on Linux. And so this is expanding it out to the ARM-based platform. We as a project, we've never done ARM before, so this is a new this is a new functionality, a new exploration. So these are the steps. I'm not going to go through in detail to actually port the OpenIFS application. So it had to be built from scratch within the ARM-based environment, requiring all the libraries and so forth to actually do it. We used a emulator. We didn't have access to the actual ARM chip for this. So we used the QEMU emulator for that purposes. So this is the arrangement on the actual car, what the client what's sent to the clients. So we have the OpenIFS code and the control code, which controls the OpenIFS. It acts as the intermediary between BOINC client and the OpenIFS code. And then the ancillary supporting ancillary files and simulation configuration files. So these are all sent to the BOINC client running on this CAN bus, or would be sent. So we built this. We built this for this environment, and we conducted some tests. And this primarily was comparing it with its performance on desktop. So the key thing is that this ARM-based environment is a lot less capacity than desktops. So which makes a big deal of difference. So we pared down. First of all, to actually make sure we get the model to fit, we picked a grid of a much lower resolution than we normally would do for our computations. This is called TQ63, which has longitudinal spacing of 209 kilometers, which is quite a coarse grid with 91 vertical levels. This reduces the amount of computation required, the amount of RAM required, and the amount of data produced. So this was reasonably what we'd expect to be able to run on such an environment. It's on the boundary of scientifically useful. That's the key thing with this. Scientists, of course, want high resolution better, basically. Always, as always. So comparing the time taken for both, on a desktop, this takes 3 minutes. On this environment, it took 3 hours. So, no, sorry, 1.5 hours. So that's a significant change. So in conclusion, we built it and done. Hang on, sorry. Okay, I clicked 2 forwards. Okay, so you can see that I'm not going to start. I'm not going to start it up again. So in conclusion, we downloaded and we built the OpenIFS application on the ARM environment, ARM platform. We downloaded it onto this QEMU emulator, and ran a sample work unit running one of these very low resolution OpenIFS simulation. The time taken to compute it was significantly longer, which is expected as it's less powerful platform, but it really makes it unviable for use in CPDN. So the conclusion really is that with future improvements of CAN bus, the CPUs on these CAN buses in the car will potentially, yeah, we'll definitely we'll be able to make it more useful, make it actually be able to produce scientifically useful results in a reasonable time. And that's very much a future thing. In terms of, I mean, there is, concluding remarks, there's certainly a synergy between, I mean, these would be electric cars that are purchased by people who are interested in, engaged with climate change studies. So there is a synergy between those between that climate change studies and the people interested in green, interested in reducing emissions, interested in that. So it has potential in the future, but unfortunately not right now. So that's my concluding remarks. That's it.
Well, thanks, Andy. We've got a few questions. First up is Oliver.
Yeah. Hi, Andy. Thanks for the great talk. One question regarding QEMU. Why did you have to use the emulator at all? So wouldn't it have been possible to run the ARM application natively on that platform?
Yes, we didn't have access to the project. We didn't actually have any chip. We weren't supplied with an ARM-based chip, or which matched what specifications matched the environment.
Okay.
That was the key thing. So it was basically a time thing. So
do you have any idea how much the emulation could have affected your performance results?
It's quite possible that it did affect the there's certainly going to be an overhead. How much, but I don't know in terms of quantifying it. What that effect. The key check, as you say, would be to run it natively on an ARM chip, which had the environment which matches what they have in their cars. So, or what the next generation cars will have. So, yeah. I certainly, I mean, it's certainly possible. It certainly would be a possible thing in the future. This, but I think at the moment it's parked. So,
okay, thank you.
Yep.
We have in chat a question from Joel. Was the increase due to data transfer rate, CPU capacity, RAM available, or a combination?
What's increased? Increase in what? Increase in what? Increase in.
Joel, can you comment? Did you mean increase in compute time?
Yeah, the increased compute time. Well, it's a much slower environment. Much slower environment. You have the overhead of the QEMU emulation. Data transfer weights, not a big deal. So it's mainly CPU and the RAM. That's another question. Our climate models need a fair amount of RAM, and that's a question of whether that would be available. But I mean, it's interesting in general because it rules out. We have discussed the idea of using Android phones, but it does very much rule out.
Android phones don't have
the use of Android
RAM. So yeah, thank you. So, you're saying it's not really transfer rates between the devices or data transfer rates. You're mostly seeing it as inherent limitations of the device itself in terms of CPU and RAM. Okay, thank you.
Yeah, thanks. Thank you.